Welcome to the fourth and final section of our talk on hyponatremia. Here we're going to focus on some of the specifics of treatment and then wrap up by going over some take-home points. So let's first start by discussing some general principles of management. It's important to keep in mind that the severity of symptoms is determined primarily by the acuity with which the hyponatremia developed, and not necessarily by the absolute sodium value itself. For example, a patient with a sodium of 100 can be relatively asymptomatic if it developed over a longer period of time. But on the other hand, a patient with a sodium of 125 could be seizing if that hyponatremia developed more quickly. So rather than just looking at the value itself to make judgments about the chronicity or the severity of the disorder, it's safe to say that if the patient is symptomatic, the hyponatremia should be considered acute, and if the patient is asymptomatic, it can be considered chronic. And the reason that patients can be asymptomatic in the case of chronic hyponatremia is that the brain is able to adapt. If given enough time, brain cells are actually able to downregulate the amount of osmotically active solute within the intracellular space. And this is a protective mechanism because it decreases the osmotic drive for water to move into cells, which helps to protect against rapid, large volume water shifts which can lead to cellular swelling. And we generally say that it takes at least 48 hours for the brain to start making these adaptive changes. So having an understanding of these concepts is important because it relates to some of the general principles of therapy. So for chronic or asymptomatic hyponatremia that's been present for more than 48 hours, we presume that the brain has had enough time to begin to adapt, and thus we want to correct this more slowly. The fear is that if we correct it too fast, a rapid increase in the extracellular sodium concentration can create a particularly large osmotic gradient and potentially lead to very rapid movement of water out of cells, causing significant cellular shrinkage. And this is precisely the pathogenesis of osmotic demyelination syndrome, which we'll touch on a little more in the next slide. For acute or symptomatic hyponatremia that's been present for less than 48 hours, we can correct a little more quickly, since we presume that the brain has not had enough time to begin to adapt. So let's focus for a minute on osmotic demyelination syndrome, otherwise known as central Pontine myelinolysis. As mentioned before, this is not caused by the hyponatremia itself, but rather by overly rapid correction of a chronic hyponatremia. And again, the word chronic is important here, because it's much more likely to happen if the brain has had time to downregulate its own intracellular tonicity. And the pathogenesis is, as mentioned before, swift movement of water out of cells secondary to an increase in serum tonicity, causing rapid cellular shrinkage. And some of the symptoms can include dysarthria, paralysis, or even coma, or the dreaded locked-in syndrome. So now let's try to precisely quantify the rate at which we want to correct. For asymptomatic, chronic hyponatremia, we want to correct at a rate of about 0.4 milliequivalents per liter per hour, and no more than 6 to 8 milliequivalents per liter over a 24-hour period. For symptomatic or acute hyponatremia, we want to correct at a little faster rate, about 1 to 2 milliequivalents per liter per hour, or until symptoms resolve. And this is typically done using hypertonic saline. But still, in all cases, we want to try not to correct more than 10 milliequivalents per liter over a 24-hour period. So now we've established our target rate, but how do we calculate it? So let's start by reviewing the fluids that are typically used for correction. We have normal saline, which contains 154 milliequivalents of sodium in 1 liter, and we have hypertonic saline, which contains about 500 milliequivalents of sodium in 1 liter. And to calculate a rate, we need to determine how much sodium we're going to be giving to the patient, and we need to know how much water that sodium is going to be dissolved in. Now importantly, keep in mind that even though sodium remains primarily in the extracellular space, when calculating how much water our administered sodium is going to be dissolved in, we have to use total body water, not just extracellular water. And this is because while sodium is primarily extracellular, water is not. Water moves freely across cell membranes in response to any change in osmolality. And thus, when making these calculations, we have to think of sodium as being distributed in the entire volume of water present in the body. So if we're going to calculate a total body sodium content for a patient, we have to multiply the serum sodium concentration times the total body water. Now let's go through an example to help clarify how to accurately calculate the correction rate. So here we have a 70 kilogram man who's symptomatic with a sodium of 120, and we want to correct at 2 milliequivalents per liter per hour. So we want to start by calculating this patient's total body water. He's 70 kilograms, and water makes up about 60% of total body weight, so we say that his total body water is about 40 liters. Next, we want to calculate his original total body sodium content. Now we do this by taking his serum sodium concentration and multiplying it by his total body water, so that's 120 milliequivalents per liter times 40 liters, and we come up with a total body sodium content of 4,800 milliequivalents. So let's say we give him 1 liter of 3% saline in 1 hour. If we do this, he would receive 500 milliequivalents of sodium in that hour, and his new total body sodium would be his original total body sodium plus 500. So that's 120 milliequivalents per liter times 40, which is the 4,800 we had before, plus 500 equals 5,300 milliequivalents. This is his new total body sodium content after the administration of 1 liter of 3% saline. And then we want to calculate his new total body water. So his original total body water was 40 liters, and now we've given him 1 liter. So his new total body water is 41 liters. And now we can calculate his new sodium concentration, which is 5,300 milliequivalents divided by 41 liters, which comes out to 129 milliequivalents per liter, and thus a correction rate of 9 milliequivalents per liter per hour. Now we wanted to correct at 2 milliequivalents per liter per hour, so we simply divide 2 by 9, which gives us 0.22. And so in our 70 kilogram man, if we wanted to increase his sodium from 120 to 122 over the period of 1 hour, we can give 220 cc's of hypertonic saline in that 1 hour period. Before wrapping up, let's briefly touch on some of the pitfalls in treatment of SIADH. It's helpful to know that patients with this condition who are treated with normal saline actually tend to get worse. And to understand why that is, let's go through a quick example. Let's say we have a patient with SIADH who concentrates her urine at 600 milliosmoles per liter. And let's say we give her 1 liter of normal saline, which contains 300 milliosmoles per liter. Now, since she's euvolemic, we can expect that she's going to excrete all 300 milliosmoles from the normal saline into her urine. But since she's concentrating her urine at 600, she's going to excrete all 300 milliosmoles from the normal saline in only 1/2 of a liter of urine in order to reach a concentration of 600. So in essence, this means that we've given her 1 liter of isotonic fluid, but she's gotten rid of all the solute from that fluid in 1/2 of a liter of urine and reabsorbed the other half as free water, thus worsening the hyponatremia. And that brings us to the end of our talk. So let's quickly wrap up by going over some take-home points. First and foremost, hyponatremia is a water disorder, not a sodium disorder. And since ADH is the primary regulator of water balance in the body, the approach to the hyponatremic patient involves asking the question, why is our patient unable to suppress ADH secretion? And in general, the history and the physical are most helpful in answering this question. It's important to appreciate that the severity of symptoms correlates more so with the acuity with which the hyponatremia developed as opposed to the serum sodium concentration itself. And lastly, symptomatic patients, in general, should be treated with hypertonic saline, but no patient should have their sodium corrected by more than 10 milliequivalents in a 24-hour period.